Hello everybody. Today we shall continue our previous discussion on spheres from three-dimensional geometry. Here we shall first consider the intersection of a straight line and a sphere. And let us suppose that the equation of the sphere is given by this kind of equation number 1, like x square plus y square plus z square plus twice gx plus twice fy plus twice hz plus d is equal to 0. Over here, we want to show that this kind of sphere will be intersected by a straight line at most at 2 points. Let us consider this kind of straight line: x minus alpha divided by L, y minus beta divided by m, and z minus gamma divided by n. What is this? This is the equation of a straight line passing through the point having coordinates alpha, comma, beta, comma, gamma. Okay, and these quantities L, M, and N, these are the direction ratios of the straight line number 2. We are going to show that this kind of straight line will intersect this sphere at most at 2 points. How can we show this result? Let us consider any arbitrary point on this straight line number 2. Over here, you see, if we consider this quantity as equal to the parameter r, this ratio as equal to the parameter r, then from the first ratio compared with this r, then from second ratio compared with this r, and from third ratio compared with this r, we will find that any point on this straight line number 2 can be written in this fashion, having coordinates. The first coordinate, or the x coordinate, would be is equal to alpha plus L into r. The y coordinate would be beta plus m into r, and the z coordinate would be gamma plus n into r. So you can say that any point will have the x coordinate like this, y coordinate like this, and z coordinate like this kind of expression, gamma plus nr. Okay, so if we put x, y, and z as equal to alpha plus lr, then beta plus mr, and gamma plus nr respectively in this equation of the sphere, then we will get this result. Over here, you see, in place of x, y, and z, we have put alpha plus lr, beta plus mr, and gamma plus nr. Okay. So we got this result. Now if we expand this result, we will get a second degree equation involving r. This kind of expression, r square with coefficient L square plus m square plus n square. Then twice r with coefficient L into alpha plus g plus m into beta plus f plus n into gamma plus h. And the remaining quantity would be the constant term. That means it is free from the variable r. So we observe that this is actually a second degree equation. This equation number 3 is actually a second degree equation involving the parameter r. And so it may have at most two real root. Okay. These two real roots, suppose for r is equal to r1, if we put r is equal to r1 over here or over here, we will get the coordinates of 1 point. Similarly, if we put r is equal to r2 over here or in this coordinates, then we will get the coordinate of second point of intersection of this straight line and this sphere. So we can say that a straight line and a sphere can have at most 2 points of intersection. And the idea will be clear from this picture. You see over here, this is a sphere, and in this sphere, this is the equation of a straight line. And one can observe that in this straight line, you see over here, in this straight line. And this at most there are 2 points of intersection over here. This might be one point, and this is the second point. Okay, so we observe that at most 2 points of intersections are there. This is a point, you see. So these are the 2 points of intersection of a straight line and a sphere. Okay, now let's move to the next topic. Over here, what we can observe a result that if suppose this is a sphere, suppose this is a sphere, and if this is a straight line passing through that sphere, then if we can say that suppose this is the point P, um, and this is the point Q. Okay, this is the point P and this is the point Q, the points of intersection. And if suppose the coordinate of this point alpha, beta, gamma, and these are the coordinates of the point capital A. All right, these are the coordinates of the point capital A. Capital A has this kind of coordinates: alpha, comma, beta, comma, gamma. That is actually a fixed point on the on this kind of straight line. Say this kind of fixed point on the straight line. Say this is the position of capital A. Then the corresponding to r is equal to r1, we will get the point P. Corresponding to r is equal to r2, we will get the point Q. And then this much distance, one can prove that if L, M and N represent the direction cosines, then this much distance will be is equal to the distance AP, and this much distance for R is equal to R2 will be is equal to the distance AQ. And one can prove that in such cases, if L, M and N be the direction uh, direction cosines, then this product would be is equal to alpha square plus beta square plus gamma square plus twice g alpha plus twice a beta plus h gamma plus d. And this is called the power of the point capital A. All right, this is called this quantity, this expression, this product. This is called the power of the point capital A. And this would be useful in the next subsequent part of the discussion. Okay. So now let's continue to the uh, next part, that is the equation of the tangent plane. Hmm. Over here, suppose this is the equation of the sphere, and this is the equation of a straight line. And any straight line, we find that any straight line can be written in as the equation number 2. And we already have proved that a straight line, this kind of a straight line will intersect a sphere at most at 2 points. This is suppose one point P, and this is another point Q. Okay. Now, if suppose this point Q moves towards the point P along this sphere, then this locus of the point or locus of this straight line will generate a plane that is called the tangent plane. Tangent plane is actually the plane that will simply touch the sphere at the point P. Okay, and it can be shown. I'm not going to show the total direction, that it can be shown that this kind of tangent plane uh, has this kind of expression. And what is this? This is actually the expression of t is equal to 0. Okay, t is equal to 0 formula. You see, originally we had the equation of the sphere where x square plus y square plus z square was there. So x square has been replaced by x into alpha, y square has been replaced by y into beta, and z square has been replaced by z into gamma. Next, twice gx, twice fy plus twice hz was there. So twice gx, twice x has been replaced by x plus alpha, twice y has been replaced by y plus beta, and twice z has been replaced by z plus gamma, and the constant term d remains same. Okay, so this is actually t is equal to 0 formula, the equation of the tangent plane, and the idea would be clear from this picture. You see, over here we consider this kind of sphere. Hmm. Over here we consider this kind of sphere, and in this kind of sphere, this sphere, we consider a point, this kind of point on the sphere, and we draw a straight line. It looks that it is a straight line, but if we look at this picture from a different point of view, this is actually a plane. Hmm. And this plane is actually touching the sphere at this point. So this kind of planes are actually tangent planes. This kind of green planes are actually tangent planes. Hmm. And the tangent plane has the special kind of property that the distance of this plane from the center, this distance must be is equal to the radius. The distance of this plane from the center must be is equal to the radius of the sphere. Okay. From this result, we can find out the condition of tangency of a plane which would touch the sphere like this. So let us consider this kind of plane. Say, let us suppose that Lx plus My plus Nz is equal to P with the equation of the plane, and this plane touches the sphere like this: x square plus y square plus z square plus twice gx plus twice fy plus twice 8z plus d is equal to 0. Okay, so we know that the equation of the sphere, if the equation of the sphere is written in this way, then then the coordinates of the center are minus g comma minus f comma minus h, and the radius of the sphere is written by square root of g square plus f square plus h square minus d. Okay, and if we find the distance of this center from this straight line, okay, if we find the distance of this center from this tangent plane, not straight line, and from this tangent plane, if we find the distance of this center from this tangent plane, then the distance becomes is equal to modulus of this kind of expression. You see, in place of L, in place of X, we are putting minus G. In place of Y, we are putting minus F. And in place of Z, we are putting minus H. And this P has been shifted on the left side so that we will have this minus of P, this kind of expression in the numerator. Okay, and the denominator is L square plus M square plus N square, because the coefficients of X, Y, and Z are L, M, and N. So over here in this fashion, we find the distance of this center from this tangent plane. And that distance must be is equal to this much radius. That distance must be is equal to this much radius. So in this way, we find the condition under which, if we take the square, we will get this result. We will find this condition under which this kind of plane given by equation number 1 will touch this kind of sphere given by equation number 2. So this is the condition of tangency of a plane. Let us now discuss the plane of contact of the tangent planes to a sphere. Okay, what is this? Let us consider the equation of a sphere. Suppose this is the equation of a sphere: x square plus y square plus z square plus twice gx plus twice fy plus 8z plus d is equal to 0. Let us consider this kind of sphere. And on this kind of sphere, we consider a point, suppose Q. This is a point Q having coordinates x prime, y prime, z prime. Q has this kind of coordinates, and this point Q lies on this given sphere: x square plus y square plus z square plus twice gx plus twice fy plus twice 8z plus d is equal to 0. Now we try to draw a tangent plane. We try to draw a tangent plane through this point Q, and this tangent plane will pass through a point the tangent plane will always pass through a fixed point alpha comma beta comma gamma. Okay, then we see that that particular position, if we change the position of the point Q, keeping this position of this point, suppose this is the point P. Hmm. Now, if we fix this position of the point P and change the point Q, then it can be found that the locus of the point Q will always pass um, through a fixed point. Okay, and that point is actually the point P. Okay, if we now change the position of the point Q, then we will find that keeping this position P fixed, and that the locus of the point Q is actually a plane, and this would be the equation of the plane, and this plane is called the plane of contact. What is the formula of this plane of contact? The formula is T is equal to 0. Okay, you see over here in place of x we have alpha into x prime, beta into y prime, gamma into z prime, plus twice g x plus twice g, and in place of twice gx we have g of x plus x prime. In place of twice a fy we have twice a beta plus y prime. In place of twice hz we have twice h gamma plus z prime plus d. Okay, so if we now consider the locus of this point x prime, y prime, z prime, all right, then the locus will be this kind of point, this kind of plane, alpha x plus beta y plus gamma z. Hmm. That is the equation of the plane of contact, and this plane of contact has this kind of formula: T is equal to 0. Okay, in order to understand this result in a bit better way, let us consider this sphere. Let us consider this sphere. Over here you see this is a sphere, and this is a point Q. This point Q lies on the sphere, and through this point Q we draw a tangent line. Okay, and this is actually the part of the tangent plane. This is the tangent plane. If you consider this plane, okay, then this as the point Q moves along this small circle, as the point Q moves along this small circle, you can observe that this kind of motion. Over here the point Q moves along on the small circle on the sphere, and the position of the point P is fixed. Okay, and therefore it can be shown that this kind of point Q will always pass through a plane. Hmm. And that plane is this kind of plane. Let me show you that the plane is a plane like this. Hmm. You see it, sorry, to this plane. This is the plane. Hmm. It is always passing through this kind of plane. All right, and this plane, this is called the plane of contact. This plane is called the plane of contact. Okay, so this is the idea of plane of contact. If you see that this plane over here, if you consider this plane, then this plane is actually the plane of contact of the tangent planes or the tangents drawn from the point P. Hmm. And if P has the coordinate alpha, beta, gamma, then the equation of this plane, this plane can be considered as the plane of contact of the tangent planes drawn from this point P. Okay, the plane of contact of the tangent planes drawn from this point P. You can check over here. You see, as the point Q moves, then the correspondingly the tangent plane will also move, and that is actually passing through the PQ straight line from this animation. And it is clear that the point Q will always lie on this kind of on a plane, and this kind of plane is actually called the plane of contact. In fact, this PQ straight line will generate a conic like this. Okay, this PQ straight line actually passes through a conic with P as the vertex and PQ as the generator, and along this generator we consider a plane that is actually the tangent plane, this kind of pink plane that is actually the tangent plane. And this tangent plane, this kind of all possible tangent planes for different position of Q, all these possible tangent planes will actually have this Q point as the point of at which the tangent plane touches the sphere. Okay, therefore we can say that this point Q will always lie on this kind of plane, and this plane will be called the plane of contact. This plane is called the plane of contact of the tangent lines drawn from the point P. Okay, this plane is called the plane of contact of the tangent lines drawn from the point P, and the equation of this plane of contact is given by this kind of equation: T is equal to 0. Let us now consider the polar plane of a point with respect to a sphere. What is a polar plane? You see, suppose this is the equation of the sphere: x square plus y square plus z square plus twice gx plus twice fy plus twice hz plus d is equal to 0. Over here, I tried to draw this picture of a sphere. Suppose this is a sphere. And now we consider a point P. What is P? P is this kind of point. Suppose this is the point P having coordinates alpha, beta, and gamma. Say this is the position of the point P. Okay, so alpha, beta, gamma, these are the coordinates of the point P. All right. Now, you see, alpha, beta, gamma, these are the coordinates of the point P. Now we can consider any arbitrary plane through the point P. You see, this plane may be considered as this kind of straight line, although it looks that this is a straight line, but we can think of this kind of plane, think this line as a plane passing through the point. Okay, and then we will have this section of a plane as this kind of small circle. Hmm. Then the section of the plane will have this kind of small circle, and at each and every point of this section, at each and every point of this section, we can draw a tangent plane. Hmm. And it can be proved that all such tangent planes are passing through a single point Q. Over here, although the picture is it should be three-dimensional picture, but over here in a plane, I am trying to draw this picture. So over here, I can show this end point and this end point. These are supposed to end points. Let me magnify this picture a bit. Say this is one endpoint and this is another endpoint. And at these two endpoints, let us try to draw two tangent planes. Suppose this is one tangent plane and this is another tangent planes. And this tangent plane, all such tangent planes through this section, through these points, through any point on the section, all such tangent planes will intersect at a single point. Taking this point Q at a single point Q, taking this point Q as a vertex, we can generate a cone where this line would be the guiding curve and Q would be a vertex. And now you see, if you fix this point P, in that case, we can change the position of this plane passing through this point P. We can consider different planes through this point P, and for different choice of the plane, the position of this point will get changed. And therefore, ultimately we will find that for different choice of this kind of plane, the point Q will ultimately lie on a plane. The locus of the point Q will ultimately lie on a plane, and that plane is called the plane of contact. Okay, over here this point Q will have this kind of coordinates, x prime, y prime, and z prime. And then this locus of the point Q, locus of this point Q will ultimately be the polar plane. Locus of this point Q will ultimately, this over here you see, and the locus of the point x prime, y prime, z prime. I'm not going through the reduction. You can look at the reduction over here. It can be proved that the locus of the point x prime, y prime, z prime, this locus will ultimately be a plane. And the idea would be much more clear if you consider this picture over here. You see, we have taken a point Q, and through this point Q, through this kind of point Q, we have taken a plane, any arbitrary plane, this kind of point, this kind of plane. This kind of plane will be any arbitrary plane, and this is the section of the plane. Okay, this is the section of the plane, section of this surface, and this plane to the point P. So this would be the this kind of a small circle. This kind of small circle will be the section of the plane. Okay, and through this section, on these sections, I have considered 3 points. You see, let us consider 3 points. Remember, this plane is actually the xy plane. Hmm. And we have considered point, we have considered a plane through this kind of point. Now on this section, I have considered 3 points. This is one point, this is another point, and this is the third point. And at through these 3 points, I have drawn uh, 3 tangent lines over here. You see, this is one tangent line, this is another tangent line, and this would be the third tangent line. All these tangent lines will pass through a point, and let us call this point Q as per our construction. So this would be the view that I discussed over here. You see, this plane, from this view, this plane through the point P looks like a straight line that I have drawn over here. You see, this kind of point, this kind of plane through this point looks that as if this is a straight line over here. So it looks like a straight line, and this small circle has been demonstrated over here. This small circle has been demonstrated by this kind of blue line, and at each and every point on the circle we can consider tangent planes. And for example, I have taken 3 points on this kind of circle, and these are the points B comma E comma this, what is this point? This is the point D. So let us consider a plane, tangent plane through this kind of point B. Let me show you the tangent plane through this kind of point B. Say this line over here. This is a tangent plane through this point E. Let me make this picture a bit simple. First of all, let me first suppress this picture. You see, if you look at this, if you look at this line, this plane is actually the tangent plane through the point E. Through this point E, that would be the tangent plane. This is the tangent plane through this point E, like this. Hopefully, this picture is now clear to you. This is the tangent plane through this point E. Now we suppress this tangent plane and let us consider this kind of tangent plane. Say this one through the point B. Say this tangent plane. Let us consider this another tangent plane through this point B. Over here you see this is the point B and this is Q BQ. And this plane is actually passing through this tangent line BQ. Okay, so this is the picture of the and this is the tangent plane BQ. And now let us consider another tangent plane CQ. Okay, this is the tangent plane. Say this is the tangent plane CQ. So you observe that all the tangent planes are actually passing through this point Q. All the tangent planes are passing through this point Q. So in order to make this in this kind of three-dimensional picture a little clear, I am not showing this tangent plane. Rather, I am showing these tangent lines. This is one tangent line B, E, and then B BQ is one tangent line, B is another tangent line, and over here now this is the tangent line CQ. So these are the three tangent lines. And the locus of the point Q. I am going to show you the locus of the point Q, and you will ultimately find that this locus is passing through a fixed plane. This locus of the point Q will pass through a through a plane, and that plane is called the polar plane. Let me show you how. I am going to show you the trace of this point Q. Okay, so let me show you the trace of this point Q. How is it moving? Say if you consider this kind of this is the trace of the point Q. You see over here we are just changing the position of these 3 points, and ultimately you will observe that these 3 points are always passing through a particular plane. Through this particular plane, and this is the plane passing through the point P. The plane is always passing through the point P, and this point Q will always pass through will always lie on a single point. Let me show you how. Let us consider a different, little smaller view over here. You see, over here these are the trace of the point Q, and it appears that the point Q is moving fine. And now let me consider the change, little small change over here like this. Let us now consider this kind of change, and it appears that apparently it looks that Q is not moving through a plane. Now this is the position of the plane. You see, if the Q does not lie on a particular plane, then from this viewpoint I would not get any straight line at all. So let me show you the particular locus of the point over here. Let me show you this plane. Where is this is the plane. Okay, the polar plane over here. Now you see I am changing this position. Now you look at this picture. Everywhere all this line that is actually the locus of the point Q, this locus will always lie on this green plane. Let me firstly suppress this plane through this point, this plane to this point P. Now consider this one. You see this point Q. This is the position of the point Q. The position of the point Q will ultimately change over here. You see, it is always moving through a single point, through a single plane. It always lies on a plane. You see all this trace. This is the position of the point Q. This trace is always lying on this plane. So from this viewpoint, it appears that the point Q lies on a single straight line. But if we change this orientation, then we will find that the point Q will always lie on this kind of plane, this kind of green plane. Okay, and this kind of green plane is called the uh, polar plane. Okay, polar plane of the point Q. Sorry, of the point P. Polar plane of the point P. Okay, and the point P is called the pole of this plane. Okay, so this is the difference. This blue point is the point. This point is the point P. Hmm. This blue point is the point P. This blue point. Hmm. So this point is called the polar of this polar plane. Hmm. And there ultimately in this way we will be able to show you that the point Q always lies on a plane, and this plane is called the polar plane. And equation of this plane, if you look at this file over here, the equation of this plane has the formula that t is equal to 0. Okay, so t is equal to 0 is the formula of the polar plane over here, and the point P is called the pole of this polar plane with respect to the sphere, of course. So that is the definition and result about the pole and polar. Hmm. Now suppose we want to find out the pole of a given plane. Hmm. In that case, we can consider that with respect to certain sphere, of course. And then we can consider that let alpha, beta, and gamma be the pole of the plane. This kind of plane, Lx plus my plus mz is equal to p. Okay, then we can say that this is the equation of the polar plane of the point alpha comma beta comma gamma, and this alpha beta gamma if we know the coordinates of alpha beta, this point alpha beta and gamma, in that case from this equation, this is the equation of the sphere. So from this equation of the sphere we can apply the formula t is equal to 0, and then we will be able to compute the equation of the polar plane, and that plane must be same as this plane by question, because it is given that this is the polar plane of the point P. This is the point P. Okay, and we can conversely say that this point P is the pole of this polar plane. Hmm. Now, as because this equation number 1 and equation number 2, as because equation number 1 and 2 both represent same plane, therefore we can say that both of these two equations are identical to each other, and so we can compare the similar terms, the coefficient of x divided by coefficient of x, then we will have alpha by L. Similarly, the coefficient of y, if we compare them, we will have beta by m. Comparing the coefficient of z, we will get gamma by n, and comparing the constant terms, we will get alpha a square by p. So that if we compute the value of alpha, beta, and gamma, then this would be the values of alpha, beta, and gamma. These would be the three values of alpha, beta, and gamma. And from these three values, we can say that alpha, beta, gamma, or this point, is the pole of the given plane with respect to this sphere. So in this way, we can find out the pole of a given plane with respect to a particular sphere. Now, to finish this lecture, let us now define the length of the tangent to a sphere. The length of the tangent to a sphere. Hmm? What is this? This is actually, suppose from at a point P, we consider this kind of point. We consider a tangent line, and suppose this PT is the tangent. Okay, and let this length, this P to T, this much length would be the length of the tangent to the sphere. Hmm? Let T has this kind of local coordinates. T have the coordinates alpha comma beta comma gamma. Then you see we as because this is the equation of the sphere, what would be the center of the sphere? Minus g comma minus f comma minus h. That would be the center of the sphere. Okay, so what would be the distance between P and T? We can apply this formula that PT square, if you consider this triangle PCT, this angle is a 90-degree angle. So this is actually a right angled triangle. So we can say that PT square is equal to the hypotenuse CT square. This is the length CT square, so minus this radius CP square. Okay, and therefore we can now say, like, compute the expression of CP square and this expression of CP square, and ultimately we will find that this PT would be actually the square root of this entire expression. Okay, so square root of this entire expression, and that square root would be like this is the length of the tangent. And you observe that this length of the tangent is actually the square root of the power of the point T with respect to the sphere. Okay, so this is the length of the tangent. Now, how to consider the normal line at a particular point? Suppose this kind of point we consider. This is a sphere, and this is a point. We can consider the equation of the sphere like this. Then tangent plane can be obtained by the formula T is equal to 0. This is the tangent plane, and this tangent plane can now be written in this fashion, that this would be is equal to x1 plus g into x plus y1 plus f into y plus z1 plus h into z plus the remaining constant terms. Then how can we obtain the direction ratio of the normal to this tangent plane? They are the coefficients of x, y, and z. These are the corresponding direction ratios of the normal to this tangent plane. So these are the direction ratios. And what is this? This is the point x1, y1, z1. Okay. So what we have to do? We have to find out the equation of the normal. What is this? This is a this straight line is actually a straight line passing through this point. This is the point P. Okay, so this straight line is the straight line passing through the point x1, y1, z1. Okay, and the straight line has direction ratios given by these three quantities. So equation of the straight line would be x minus x1 divided by x1 plus g, this first direction ratio, that is equal to y minus y1 divided by y1 plus a, that is the second direction ratio, that is equal to z minus z1 divided by z1 plus a, that is the third direction ratio. So in this way, we will be able to compute the equation of the normal. So that's all for today's lecture. We discussed different concepts related to tangents and normals over here. Thank you for being with me.